how to solve the practice questions, right? So first we'll talk about the node coverage. So if you look at this uh, particular graph, the question is like, what are the things we need to cover here, right? So if I say node coverage, so the coverage requirement, so we write it as a tier, right? We called it as a test requirement. So what are the things we need to test? So we need to test the coverage for node 1, node 2, and node 3. So those are the requirement we need to test for coverage, right? Okay. So this is the test requirement. What are the things I need to cover? So the node number 1, node number 2, and node number 3, what we need to cover. Now we need to find out what could be my test path, right? What could be my test path? So if you look at the path, I go to 1, go to 2, go to 3. If I consider the path 1, 2, 3, if I consider the path like that, I basically cover node number 1, node number 2, and node number 3. So it gives me a node coverage. It gives me a node coverage, right? Now, if you want to say, I'll consider this particular path over here. If I consider this particular path, what will happen? So this path is 1, 2. If I consider this path, does it makes a node coverage or not? It covers path the node 1, it covers the node 3, but does it cover 2? No. So this path do not give you a node coverage, whereas this gives you a node coverage, which covers 1, 2, and 3, right? So this is a path which will give you a node coverage. We say it's a node coverage path, and this is your test requirement in case of node coverage. Okay, let us go for what is the edge coverage. So if I want to go for a edge coverage, what is my criteria? If I considering edge coverage, so what are my criteria? So I want to say test requirement. So what is my test requirement? So my test requirement, I say I have to test the path 1, 2, right? So this is the path I need to test for. Then I have to test the path 1, 3, 1, 3. And I have to test the path 2, 3, and 1, 3. So these are the 3 paths what I need to test. Okay. So now I need to test this edge. I have to test this edge. I need to test this edge. So these are the 3 edges I need to test. I'll just clear my screen. It will be easier to understand the thing. So I'm looking for coverage of this particular edge, and this particular edge. Right. Now, if I take a path which is 1, 2, 3. So 1, 2, 3 provided me a node coverage we have already seen, but does it give a edge coverage? So I go to 1, then 2. So it covers this particular edge. So this is done. Then 2 to 3. This edge coverage also done. But does it cover this edge? No. Right? So this path alone do not give the complete edge coverage. So this path along with the path 1, 3, that gives you a edge coverage. So my test path for edge coverage should be this, right? Now remember, a edge coverage covers node coverage, but a node coverage may not cover edge coverage. What does it mean? This is the test path which is providing a node coverage, but you have seen this is not providing a edge coverage. But in some cases it may happen, right? We can see afterwards. There could be some cases where it is true, right? But if you have edge coverage, a test path which is providing the edge coverage, that must fulfill a node coverage also, because here the paths, the set of paths also include this particular path which provide us the node coverage. So every edge coverage also cover a node coverage. We'll see more examples. This is basically about the edge pair coverage. We'll see it in more details with a complete graph kind of thing. So let it be, we'll start with this, right? So we are having a big graph, right? So we need to do the thing. Okay. So if you consider the node coverage, so how many nodes we have? If you consider the nodes, we are having 1, 2, 3, 4, 5, 6, 7 nodes, right? So these are the nodes 1, 2, 3, 4, 5, 6, 7. So now the simple way to understand node coverage means I'll cover each of the edge, right? Each edge, each of the node will be covered, right? So there are 7 nodes. So I have to cover all the 7 nodes. I need to select paths like that. So how I can cover that? It's a simple way how I can cover all the nodes. So if I have to cover all the nodes from 1, I can go like this, right? Then I can go like this. And then I can go further like this. I can go further like this, right? This could be one path. Then another path could be, so still it is not a node coverage because you have covered only 1, 2, 3, 4, 7, right? So another way you can go 1 to 3, you can go 3 to 5, 5 to 6, 6 to 5, then 5 to 7, right? So it gives you a complete node coverage. So if you look at the path over here, so it's basically 1, 2, 3, 1, 2, 3, 4, 7. So it's a 1, 2, right? 3, 4, 7. So this is one path from the initial vertex to initial node to the end node, the termination node. And this is 1, 3. This is 1, 3. Then 3, 5. Then 5, 6. 6, 5. Then 5, 7. Right? So this cover all the nodes. Now the question is here, does it also cover all the edges? If you list out the edges, how many edges we have? So I suggest whenever you are counting the edges, please write down in this way so that you do not make mistakes. So let us first put down the nodes which starts, put down the edges which starts with 1. So that's 1, 2 and 1, 3, right? Then from 2. So from 2 you can have 2, 3. Then from 3 you can have 3, 4. And you can also have 3, 5. Then from 4, you can have 4, 7. There is no other thing. Then from 5, what you can have? From 5, you can have 6. And 5, you can have 7. From 6, what you can have? From 6, you can have 5. No node from 7 because 7 is the end node. So if you look at over here, so it's a 1, 2, right? Then 1, 3, 2, 3, 3, 4, right? Then 3, 5, 4, 7, 5, 6, 5, 7, 6, 5. So these are the edge I have to cover. So first, I already got the path which is providing me a node coverage, right? So first I can check, does it also cover the edges? So you can see it basically covers all the edges, right? So this is the path which covers the node criteria as well as also cover the edge criteria. So as I told, path, a set of paths which is covering the nodes criteria may or may not cover the edge criteria. So here it is covering, but it is mandatory edge coverage criteria will the paths covering the edge criteria also cover the node criteria, right? So it's like that. Okay. So now we'll go for the edge pair coverage. So for edge pair coverage, I'll take a minute. I'll just have a blank sheet so that I can explain this properly. So I'll just stop sharing it. Okay. Okay. I got something where I can write. Okay. So I got a blank sheet. So let me have the graph on the sheet. So it's a 1, 2, 2 and 1, 2, 3. So let me draw it quickly. So 1, 2, 2 and 2, 2, 3. Then I have 2, 2, 3, 2, 2, 3. Then I have 3, 2, 4. So here I'll have also a 4. I have 3, 2, 4. Then I have 4 to 7. 7 is a terminating node or a end node. So it will be on a double circle. This is an entering node, which has to be presented like this. Okay, then there is a 5, right? And we can have a 6. So this is like this. I think I have drawn it correctly. Okay. Okay, so let us take down the edge pairs, right? Okay. So I use edge pair criteria. I use the edge pair criteria. Okay, so what is my test requirement? So what are the things I need to cover? So I take each edge pair. So starting from 1, I take 1, 2, 3. There is a edge. There is a edge 1, 2, 3. Right. So it's a 1, 2, 3. Right. 1, 2, 3. There is a edge. Then it could be from 1, 1, 3, 4. 1, 3, 4. Right. Then it could be 1, 3, 5. 1, 3, 5. Okay. 1, 2, 3, 1, 3, 4, 1, 3, 5. There is no other 3 path from starting from 1. From 2, where I can go. From 2, where I can go. From 2, I can go 2, 3, 4. Okay. 2, 3, 5. Is there any more path from 2? No, I'm not getting anything. So let us start with 3. So 3, I can get 3, 4, 7. I can put 3, 4, 7. So this reached the end. So there is no way I can go beyond this. So it's a 3, 5, 7, 3, 5, 7, right? These are with 3, 3, 5, 6. There is one more, right? 3, 5, 6. Okay. With 5, can I have something? Sorry, with 4, can I have something? 4, 7. But there is no more extension because 7 is the end, right? So with 5, can I have? With 5, I can have 5, 6, 5. So it's becoming a loop, right? Then there is no more. With 6, can I have anything else? With 6, I can have 6, 5, 7. I can have 6, 5, 7. 6, 5, 7. So I have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let me check out. Might get the correct thing. Yeah, that must be okay. Here all everything is not written. So let me also design the test paths. So what should be my test paths? Okay, so how do I take it? Let me start with 1. So I'll have 1. So path should be something which is I should have number of paths which should cover all of this, right? So I can start with 1. Then see there is a 2, 3. So with 2, 3, I can go to 4. So basically these two are covered, you can understand. Now with 3, 4, with 3, 4, you can go to 7. So just I'll note it down properly. It's a 1, 2, 3, 1, 2, 3, then 4. Then from 4, I can go to 7. Then using 4, 7, where I can go, as a 7 is the end. So this is the path. So let us check out. It is 1, 2. It is 1, 2. Then 2, 3, right? Then 3, 4. Then 3, 7. Right. So I got this path, but still you can find out all the pairs are not covered here. So I need to still go for more paths. So paths may be given in a square bracket and it's a set. So I'll put it in a flower bracket. Okay. Okay. So can I have more paths? Okay. So starting with again 1 with 2, 3. See, using 2, 3, I can go up into 5 also. It's a 2, 3, 5, right? So this is covered. So with 3, 5, with 3, 5 also I can go to 7. Okay. So this is another path which covered this, this, this. So what is the path? 1, 2, 1, 2, 2, 3, right? Then 3, 5, 3, 5, 5, 7. So this is another path I'm getting, right? So can I have more path? Yes, I can have more because it is yet not done. So 2, 3, do I have 2, 3 anywhere? No. So let us check for this. This say I start with 1, then I go 3 and 4. Means I'm selecting this path. From here, I'm going through this path, 3, 4. Okay. So I'm having 3, 4, right? So using 3, 4, if I have 3, 4 over here, I need to check, do I have anything starting with 3, 4, right? So here I have 3, 4. So there is a 3, 4, 7. So 3, 4, 7, there is a path. So this is the path which goes like this, right? Okay, I can find more. So there is a path which go like 1, 3, 5, means it is expanding like this. It is expanding like this side. So it is 1, 3, 5. So with 3, 5, starting with 3, 5, what I can get. So with 3, 5, I can get 6. With 5, 6. With 5, 6, I can again go to 5. And with 6, 5, I can go to 7. Okay, so it is 1 3. So this is the path 1 3, then 3 5, then 5 6, then 6 5, then 7. So as you can see, everything is marked over here. So I suppose I have covered everything. If you want to cross check, it's always better to cross check the thing. So is this covered? 1 2 3, it's there, it's covered. 1 3 4, is it covered? Here it is 1 3 4, it is covered. 1 3 5, is it covered? Yes, it is there, it is covered. 2 3 4, is it covered? 2 3 4, yeah, I have it over here. 2 3 4, it's covered. 2 3 5, 2 3 5 is here, so it is covered. 3 4 7, 3 4 7, it's here. 3 5 7, so 3 5 7, 3 5 7 is here, so it's covered. 3 5 6, 3 5 6 is here, covered. 5 6 5, 5 6 5 is here, it's covered. 6 5 7, it's covered. So this gives you the path coverage. Now, as we discussed, path coverage automatically covered. Uh, sorry, it's a H pair coverage. It's a H pair coverage. So H pair coverage automatically covered the H coverage, as well as it also covers the node coverage. So the simple way understand. So node cover edge is covered or subsumed by edge coverage, which is covered or subsumed by edge pair coverage. Right. So this is how we should go for it. Okay. So let us go for next. There is something called as a complete path coverage. So complete path coverage means for you have to go for all possible paths. If you look at a simple graph which do not have a loop, suppose I take just 1 2 3 4, and I'm having some paths like this, edges like this. So it is fine to find out the complete path coverage, because you know this is 1 2 4 could be one path, and another possible path could be 1 3 4, right? Because you're supposed to have finite number of possible paths, right? But if you have some kind of graph like this which is having a loop, the problem is you can have an infinite number of paths, because if you go 1 3 5 6 5 7, so you go 1 3 5 6 5 7, it could be one path. Then 1 3 5 6 7, 5 6 5, then again 6 5, repeating twice to 7, another path. Again you can have 1 3 5 6 5 6 5 6 5, then 7, repeating 3. So I can repeat it n number of times and I can generate a n number of paths. So there is no limit. It could generate infinite number of paths. So basically, if I don't have a loop, a complete path coverage makes a sense. Otherwise, complete path coverage is not basically feasible. So that's why we go for a different kind of coverage, which is called as a prime path coverage. Okay. So this is the first example which is considered for prime path coverage. I want to start with that. Before that, just 1 minute, give me a minute. Okay, let us have it, start it. Okay, uh, sorry. Okay, so this was the thing, graph we are discussing. So let us draw the graph first, then I'll explain the thing. Okay, so what I have in the graph, it's a 1, 2, 3, 4. Okay, so let me have it. Yes. So I have 1, 2, 3, 4. Okay, so the path I have, it's a 1, 2, 1, 3, 3, 4, 2, 4, right? And I'm having this. Okay, so this is my path. Now we say it as a prime path coverage. So to understand prime path coverage, you need to understand one term that's called a simple path. So what is a simple path? Just I'm showing over here. If you look at this, any path inside the graph where nodes are not repeated, right? Any path where the nodes are not repeated, it can be only repeated if the starting and the ending vertex or node of the path is the same. That is the only time your node could be repeated. Otherwise, it never could be repeated, right? So 1, 3, 4 could be a path which is a prime path, right? Again, 1, 2, 3, 1, 2. So again, I just let me write it. 1, 3, 4. Right, 1, 2, 4 could be a simple path because none of the nodes got repeated. If I say 1, 2, 4, this is a simple path because nothing is repeated. If I say 1, 2, 4, 1, this is also considered as a simple because the starting and ending nodes are repeated. So either I don't repeat anything or only the starting or ending node will be repeated. None other than those nodes will be repeated. So what I cannot do, any intermediate node cannot be repeated. Like if I have like this, I cannot write it 1, 3, 3, 4. This is not possible. This is not a simple path, correct? But I can have always a simple path 3, 3 because ending node and starting node are same. That's fine. But intermediate nodes cannot be repeated. They have to be unique, right? Okay. So please try to understand how to do it clearly. So I write it, I solve it like this. It's a L0. So I want to find all the paths which are having length 0, right? So that's basically the nodes. So which are the nodes I have? It's a 1. So if I'm on the same node, the length of the path is 0, right? 1 to 1 is a 0 distance. Then it's a 2. Then it's a 3. Then it's a 4. Right? So these are the things. Okay, I am having a end node, right? So here let the end node is 4. Now, whenever you are marking this, you have to mark the end node as this, right? We use a exclamation marks to say this is my end. From here, I cannot expand. From here, I cannot expand because in each iteration, I'll increase the length of my path and I'll try to find out what could be my largest maximum independent path. But how long it could be? So as you can understand, if you have 4 nodes, the maximum path could be, the size of the path could be 3, right? The length could be 3. So I have to check for length 3, all the paths with length 3. So this is L0. The paths with length 0 means the nodes like 1 to 1, 2 to 2, 3 to 3, 4 to 4, like the node itself. Then L1. So distance L1 from 1, how I can expand from 1 to distance 1? So it could be So let it write it on a square bracket because path will write in a square bracket. So it's a 1 to 2, or I can go to 1 to 3. So this is, we can have extend from 1, I can go to 2, 1 to 3. We're taking length 1 only. Then from 2, where I can go? I can go 2 to 4. From 3, where I can go? From 3, I can go to 4. And 4, I'm sorry, I drawn it wrong. Actually, the final vertex has not given here. So that's the problem is. So actually, this 4 cannot be a final vertex, right? Because see, there is a path from 4 to 1, right? So 4 cannot be a final vertex. So that's the problem. So with this, doing finding a prime path is very difficult because there is no defined kind of starting and ending index. So let me do it in another way. Let me take all the simple paths we can have like this, right? So as here solved it, the simple path we can have like this. See, we can have it like uh, let us take from the smaller thing. I can have 1, I can have 2. I'll show the thing with another example because this is not an ideal example for showing this. So 3 and 4. So this is with length 0, right? How what I was telling. Then length 1. From length 1 means starting with 1, what I can have? 1, 3, 1, 2, 1, 2, and 1, 3. With 2, I can have 2, 4, right? 2, 4. Then I can have, are you getting or having problem? Shall I go for the image? Okay, let me do it with the images only. So I think it will be easier. Let's forget about the final. Okay. So it's a 1, 2, 3, 4. So these are my with length 0. With length 1, what I can have? Length 1, I can have for 1, I can have 1, 2. So I can have 1, 3. So these are all simple paths. I'm listing all simple paths. Because whenever I list the path, you'll find the intermediate nodes are not repeating. Only the start and end node could repeat. Okay, from 2, how we can have such node? We can have 2 to 4. We have already discussed that. Then from 3, what you can have? You can have 3 to 4, right? And from 4, what we can have? 4, we can have 4 to 1, right? This is what I can have. Then with length 2, what I can have? So from 1 to what I can have first? From 1 to, I can have 1 to 4. 1 to 4. Can I have anything with 1 to? No. 1 3, I can have 1 3 4. 1 3 4. Can I have any more with 1 3? No. So with 2 4, can I have anything? So with 2 4, I can have a path. I can have 2 4 1, right? 2 2 4 1, length 2. It's a length 2. Okay. Can I have more with 2 4? No. With 3 4, can I have anything? With 3 4, I can have 3 4 1, right? 3 4 1. With 4, can I have anything? With 4, I'll consider 4 1 2. I can consider also 4 1 3. Okay. So since the number of nodes are 4, so maximum length of the path I have to consider, that's a 3, right? That's a 3. So I can check for L3 now, right? So with 1, 2, 4, what I can have with the length 4? 1, 2, 4, I can have 1. My first node could be repeated, so it's valid. From this one, I can have 1, 2, 4. Then I can have 1. It is still a simple path because like this, but if I still extend it, then it won't become a simple path. But anyhow, I have reached the maximum because this is for length 3. So 1, 3, 4. Can I have any extension of this with length 3? So 1, 3, 4. 1, 3, 4. I can repeat 1, right? Okay. Now 2, 3, 1. 2, 4, 1. Sorry. With 2, 4, 1. It's a 2, 4, 1. I can have 2. So it's the end vertex is repeating. It's fine, right? And any more with 2, 4, 1? With 2, 4, 1, I can have also 3. That's also fine because none of the vertex got repeated, but there is no more with 2, 4, 1. Anything with 3, 4, 1? 3, 4, 1. 3, 4, 1. So I can have 3, 4, 1, 3. So the end vertex are repeated. That's fine. 3, 4, 1, 2. That's also fine. 3, 4, 1, 2. That's also fine. Now, can I have anything with this? 4, 1, 2. So if I consider 4, 1, 2, then 4 is repeated. The end vertex repeated, it's fine. 4, 1, 2, 4, 1, 2. So there is no extension, more extension, but 4, 1, 3, 4, 1, 3. I can have 4, 1, 4. 4, 1, 3, 4, right? Length 3. See, we cannot have more because for any of this path, if you want to extend, it won't become a simple path. So if you will check for 1, 2, 4, 1, 1, 2, 4, 1, either if you go for 2 or 3, this 1 will be repeated and it becomes an intermediate node because the 3 or 2 or 3 will come after the 1, right? If you just take any arbitrary node here, so that's the problem, right? So it won't become a simple if you extend anymore. So that's the maximum, right? So that's the maximum. So this is the maximum length what you are getting. So this path with maximum lengths, the paths with maximum lengths are basically considered as a prime path. So in this case, these are the paths which are having the maximum lengths, right? So this is length 3, this is length 2, this is length 1, length 0, right? So what are your prime paths? Let us mark here. So these are all simple paths with maximum length. So we can go like this: 1, 2, 1, 2, 2, 4, right? 4, 1, right? So this is a simple path. It's basically representing a loop. And if you've gone through the prime path coverage from the lecture, you must be knowing this is the best to test the loops, right? Okay, let me take a different color. So it's a 1, 3, 4, 1. So it's a 1, 3, 4, sorry, 4, 1, right? So it takes another path. But again, this is a loop. Okay. Okay. So 2, 3, 4, 2. So I start with 2 now. So 2, sorry, it's a 2, 4, 1, 2, 2, 4, then 1, 2. Again, it's a simple path: 2, 4, 1, 2. But you can definitely find out if I try to extend any more, then it will be a problem. The 4 is the intermediate node which will be repeated. So it do not become a simple path. So you can trace all the paths, each will give you a simple path, and which is an independent path, right? Okay. So we'll go for more examples if we have. Okay, so this tools and all, I'm not doing it right now. If you have problems with this, we can go for it afterwards. I'll just go and check out if I have any more examples in the slides. So I'll just explain that example. Yeah, I got a big one. So let us go for this. Okay, you can see this graph, I think. So we are going to cover through a prime path. So here this node coverage, edge coverage, and edge pair coverage are very simple, as we have seen. So only a bit complicacy arise whenever it's a prime path coverage. So prime path coverage, I'm going into little more detail. Okay, so let's clear the screen. Something of my last class. Just give me a minute. Okay. So first, the difficult part of it, I need to draw it again. So it's 0 to 1, 0 to 4. So, okay, it's a 0. Let me take some different color. It should be visible. It's a 0. Okay. So it's the entry. This is the initial node. It's called the entry node. Entry node, right? Then you have 4. Right. So there is a loop. Okay. Then we have a 1. Okay. We have 5. Okay. Then there is 6. So this is 0 to 1, 1 to 5, 5 to 6, and 4 to 6. And there is R2, and there is a 3. Okay, so okay, so I have a loop here and here, right? It's a self loop. This one is a self, right? Okay, so let us try to figure it out quickly. So how do I do it? So here I'm having clearly a entry node and terminating node. That's a 6. So let us first write what should be my L0. Path 0, right? So that's node 0, node 1, node 2, node 3, node 4, node 5, node 6, right? One. There are 7 nodes. I'm starting from 0. So if I have 7 nodes, so I have to check maximum path length. That's basically a L of 6. Up to L of 6 I have to go, which is quite long. Let us find out how long we have to go. maybe it could be closed further before that. Okay, so I use some symbols here. So if path have no way to extend anymore, so I put it a exclamation. So that's the end. So that path cannot be extended further. And if I want to loop, then I'll also stop over there, because rather than repeating the loop, I'll just cover the loop once. So I'll mark it with a star. So one node cannot, I don't have any loop. So, but I'm having a terminating node, I have marked that. So I have L1. So with 0, what I can have? With 0, I can have 0, 1 and 0, 4. Right? Okay. Now from 1, what I can have? From 1, I can have 2, 1 to 2. I can have 1 to 5, 1 to 5, 1 to 2, 1 to 5. That's all. Now with 2, can I have anything? I can have 2 to 3. Okay. Anything? Okay. With 3, I can have 3 to 1. Right? With 4, I can have 4, 4. This is a loop which I marked with a star. So that means I won't repeat this loop. And with 4, I can have also a 4 to 6, which is also terminating here. So there is no extension further. With 5, I can have 5 to 6. That's also ends over here. Okay, so these 3 nodes I don't have to deal with anymore. I have to deal with rest of the nodes because those could be further extended. Right? So let us go for L2. Why I don't extend the self loop? Say if I extend it to 4, 4, 6, it won't become a simple path, right? Because 4, 4, the intermediate node will be repeated. That's not the node. Only the node could be repeated, not repeat. I'll say the first node or last node could be the same, right? That's the only thing. The first node and last node could be the same, which is okay here. But if I write 4, 4, 6, then it's a not correct. It's not a simple path, right? Okay, so let us go for checking all other paths. So 0, 1, what could be my extension? For 0, 1, I can have a 0, 1, 2. I can have 0, 1, 2. I can have 0, 1, 5. I can have 0, 1, 2, 0, 1, 5. 0, 4, right? I can have 0. I cannot have 0, 4, 4, right? Because it is not a simple path, but I can have 0, 4, 6. That's fine, but it's the int. So with 0, 1, just let us check it. 0, 1, 2, 0, 1, 5. There is nothing, right? With 0, 4, you can go 0, 4, 6. Okay, let us check for 1. So I have 1, 2, 3. I have 1, 2, 3. Can I have anything more with 1, 2? No. With 1, 5, I can have 1, 5, 6, which is the end. 1, 5, 6 is the end. There is no more with 1, 5. That's all. And 1, 2, only one path. Let us check for 2, 3. So I can have 2, 3, 1. 2, 3, 1. Right? 2, 3, 1. I cannot have anything with 2, 3. Can I have anything with 3, 1? Where is my 3, 1? I have 3, 1 here. I can have 3, 1, 2. 3, 1, 2. That's fine. 3, 1, 2. That's fine. But there is nothing with any more than 3. Okay, 3, 1. I can have 3, 1, 5 also. 3, 1, 5 also. So let us check once more with 3, 1. So 3, 1, I can go like this, I can go like this. Yeah. So this 3 I don't have to do because these are already done. Here also this is already done. I don't have to do. So I have to check for now L3. So I'm doing L3 over here, but whenever you will solve it, do it in a proper manner because it's very error prone kind of thing. Like whenever you're doing manually, because number could mix up and creates a lot of them. So 0, 1, 2, 0, 1, 2, 3. I can go with the 0, 1, 2. I can go to 3. So let us check with 0, 1, 2. Can I go anywhere else? No. Okay, so now 0, 1, 5. 0, 1, 5. I can go to 6, right? 0, 1, 5, 6. So that's end here. This is I cannot go further. That's already end. Now 1, 2, 3. Can I go anymore? 1, 2, 3, 1. So that's a star. 1, 5, 6. 1, 5, 6. That's already ended. Oh, I don't have to take this. It's a 2, 3, 1. A 2, 3, 1, 2. So let's make it on the same different line. It's a 2, 3, 1. With 2, 3, 1, what I can get? With 2, 3, 1, I can get 2, 3, 1, 2, which is a loop, or I can go to 2, 3, 1, 5, 2, 3, 2, 3, 1, 5, right? Anything more with 2, 3, 1? No, there is nothing. I can still have with 2, 3, oh, 2, 3, 1 is done. 3, 2, 1. I need to check for 3, 2, 3, 1, 3, 1, 2. So it's a 3, 1, 2. So 3, 1, 2, it's again a 3. So it's a loop. Okay. So which is left? I'm left with two paths here, this and this. So I have to go for L4. I'm writing L4 over here because I need to see this thing visible. I have to keep, but I have to do it for this path and this path. Only these two left. So it's a 0, 1, 2, 3, 0, 1, 2, 3. See, if I have to repeat, I have to go back to 1. So it no more remain a simple path. So actually that path is already ended. If you look at, so you can just put an exclamation mark over here. Again, I say why I put exclamation mark. If you say 0, 1, 2, 3, I cannot extend it. If I try to extend it again, 1 will repeat, which is the intermediate node already. So it no more remains a simple path. And there is no way to come out without 1, right? So it's basically ended over here. So one path only I can extend. That's basically a 2, 3, 1, 5. So 2, 3, 1, 5, that ends with a 6 clearly. So I'm getting clear. So which are the path you need to finally consider to find out the test requirement or the prime paths? So your prime paths would be this, right? Would be this, this, which are ended with a star or ended with a exclamation mark, this, then this. So these are all your prime paths. Okay. So this is what is been done. Now, how to compute the prime paths? Right. So these are the paths which I considered as a prime. So I'm getting 8. So let us just count it. So this L0 I won't consider. I haven't marked it. So what I have took here, 4, 4, Okay, I need to take so that they're independent also. So it's better to start with the maximum path. Uh, Let us write it down somewhere else here. So I take the start with the maximum. Why I start with the maximum? This is one prime path. This is I'm getting at the end. Now I have to check all the paths which are with star or exclamation. This is 3, 1, 2, 3. So I need to check if this path is already a subpath inside this. 3, 1, 2, 3. No. So I have to consider this path also. 3, 1, 2, 3. So I have covered this. Okay. Now this path, this is also star. I have to check this. 2, 3, 1, 2. 2, 3, 1, 2. 2, 3, 1, 2. No, I haven't covered. 2, 3, 1, 2. Okay. I have to check for this. It's a 0, 1, 2, 3. I don't have any path with 0. 0, 1, 2, 3. And also 0, 1, 5, 6. 0, 1, 5, 6. So I already have 1, 2, 3, 4, 5, 5 paths. Let us find out still if we have. Now with length 2, what we have with exclamation mark, we are having 1, 5, 6. 1, 5, 6 already is subpath over here. So we don't have to take it separately. 0, 4, 6. Is it path somewhere? No. So I need to consider 0, 4, 6. Okay. Now I go for the length with 1. 4, 4. It's not a subpath of any of this path. I take straight 4, 4. 4, 6. Do I have 4, 6 anywhere? Yes, 4, 6 here. So I don't have to take this. 5, 6. Do I have it? Yes, I also have this. So how many I'm getting? 1, 2, 3, 4, 5, 6, 7 paths. I supposed to get 8. Let me check out once again. I got this 1. I checked for 3, 1, 2, 3. Yes, I have added this. I have checked for 2, 3, 1, 2. 2, 3, 1, 2. Yes, I have this. 1, 2, 3, 1. 1, 2, 3. Yeah, I forget to add this. 1, 2, 3. Yeah, this is not there. 0, 1, 2, 3 I have. Then 0, 1, 5, 6 I have. Yeah. So these are the 8 prime paths which cover all the simple paths. Now from the prime paths, how do you derive the test paths? Now question is, what is your test paths? What are your test paths? Just before I go into it, I'll just repeat once again what I have done before to find out my prime paths. After putting all the lengths, so here I have end because here I don't have any path to extend anymore. But I start with the maximum path because prime path should be the maximum simple paths. I take this. Then I take all other simple paths which are on maximum. So I take this. It is not covered by this path. So I add this. This is also not covered. This is also not covered. This is not covered. So I'll just add them as it is. But whenever I'm considering this 156, I saw this 156 already covered. So already, although this is a simple path, I don't have to consider this because already this is a path of a existing prime path, right? So like this, you need to consider all the nodes which are with this or asterisk. If they're a subpath of already existing prime path, we don't have to take it. Otherwise, just write it down. Okay, how we'll create the test paths? So all these are sets. This is prime path, set of prime paths, right? So test path again, we need to start with the biggest path. So it's a 2, 3, 1, 5, 6. So 2, 3, 1, 5, 6. So you have to complete the path. 2, 3, 1, 5, 6. How do you complete the path? Just if I make it 0, 1, 2, it will be a complete path, right? So I can make it 0, 1, 2, 3, 1, 5, 6. So this could be one path. Just 0, 1, 2. Just 0, 1, 2, 0, 1, 2, 3, 1, 3, 1, 5, 6. 5, 6. It is like this. Okay, so I got one test path. Now, if any prime path already covered into the test path, I may avoid that one. Now, 3, 1, 2, 3, is it covered? 3, 1, 3, 1, 2, 3, no, not covered. So 3, 1, 2, 3, I need to look for. Where is 3, 1, 2, 3? So 3, 1, 2, 3. So 3, 1, 2, 3, it basically shows a repetition, right? 3, 1, 2, 3. Right. So I have to go 0, 1, 2. I have to go 0, 1, 2. Then I get 3, 1, 2, 3. So let us find out 0, 1, 2, 3, 1, 2, 3. Then 1, 5, 6. That's the end, right? Then I have to add 1, 5, 6. That gives you another path. It's a big path, right? So let me take another color. Let me draw this 0, 1, 2. So it's a 0, 1, 2, right? 0, 1, 2, then 2, 3, then 2, 3, 3, 1, 2, 3, 1, 2. So it's repeating the loop, you can understand. 3, 1, 2, 3, 1, 5, 3, 1, 5. It's repeating the loop twice, then 6. So it is basically exercising the loop number of times. The first one exercise for one time, this is for 2 times. Right? Okay, so I have covered this too. Let us go for this. This is 2, 3, 1, 2. I have to check it is already covered. So 2, 3, 1, 2 is already part of this. So this is already done. So this is already a subpart of this. So I don't have to do this. 0, 1, 2, 3. 0, 1, 2, 3 also done. So this is also done. 0, 1, 5, 6. 0, 1, 5, 6 not done. So it should be a unique path. 0, 1, 5, 6. So it's I'm getting a complete path here. 0, 1, 5, 6. So you can check out. We already get the paths which is skipping the loop, which is skipping the loop, which is repeating the loop once, which is repeating the loop twice. So it's exercising my loop for different check conditions, right? Then I have 0, 1, 5, 6. Oh, I have done already. 0, 4, 6. Let us check 0, 4, 6. Do I have? No. So 0, 4, 6 again an independent path. Yeah. 0, 4, 6. I have a 4, 4. So I can have this 0, 4, 4, 6. So you can understand 0, 4 skipping the loop, right? And 0, 4, 4, 6 with iterating the loop, right? Then last one is 1, 2, 3, 1. Just check out 1, 2, 3, 1 is already sub. So this is my test path for prime coverage. Okay, so next what we'll do, quickly glance through the practice questions. Give me a minute. So we'll cover it quickly because most of the questions are theoretical only. So the first is, which is the best representation that an edge is reachable? Our edge is having the vertexes u and v. So I think now it is visible, right? Yeah. So the options, the edge is reachable if there is a path from one initial vertex of to vertex u. No, it's basically both the nodes must be visible from the initial node, right? Then only the things. So the B option is correct because it says E node is reachable. The E path, sorry, edge is reachable if there is a path from one initial node to the vertexes u and v both. Right, that's the thing is. Now next is a structural coverage criteria on graph is described by which of the following. So it's basically using the particular artifacts could be presented using nodes and edges only. You don't have to have anything else inside the thing. So the one option A is correct. So only using node and the edges will be able to cover everything. So you have seen for the node coverage, edge pair coverage, prime coverage. We just draw the nodes and edges. That's all. Nothing else. Okay. Given a graph corresponding to control graph of a method, which option below define a reachable node? So reachable node is something which is reachable from the initial node, any of the initial node, if I have multiple initial nodes, right? So a node is said to be reachable if there is a path from any other node to that node. No, that's a connected node. Two nodes are connected, but that doesn't, it's a reachable node. Reachable node is the option B, right? The node is said to be reachable if there is a path from the initial node to the node in the graph, the target node. Initial node to the target, there should be a path. Then only it's a reachable node. And for reachable path, both the vertices should be reachable from the initial node. So there must be a path to both the vertices, both the nodes. State true or false in control flow graph corresponding to the function or method, strongly connected components corresponding to the loops. Yes. So inside the loop, the nodes are called strongly connected components. So this is the subsumptions criteria. So what I was calling about the covering. So I say the node coverage subsums or cover the edge coverage subsums edge pair coverage. So the correct way to say the edge here, this is the subsumption symbol. The prime path coverage cover the edge coverage subsums the node coverage. Because what you can cover using a node coverage, same thing could be covered, same or more could be covered using edge coverage. Right. So if you have edge coverage, you can guarantee the node coverage, but reverse may not be true. If you have a prime path coverage, you can guarantee edge coverage, but reverse is true. So if you look the entire hierarchy, so node coverage is subsumed by edge coverage. Edge coverage is subsumed by edge pair coverage. Edge pair coverage is subsumed by prime path coverage. Or another way, node coverage is covered by edge coverage. Edge coverage is covered by edge pair coverage. Edge pair coverage is covered by prime coverage. Now this is the graph for which we have few things. So let us have this graph in our mind. So we'll come back again after reading the question. State true or false. There is a test path that achieved node coverage but not edge coverage. So for this graph, can I have a edge coverage path set that do not do a node coverage? So if I look into this particular graph, there is only one path, I assume. So you have to always go like this. Oh, there is another one. There is another one. You can also go like this. Yeah. But if you want to go for a edge coverage, which path will go for? So if I want to have a edge coverage, the path will go for, that's a 1, 2, 3, 4. So this will give you a edge coverage, right? 1, 2, 2, 3, 3, 2, 3, 4. So this, along with the edge coverage, also guarantee node coverage, because edge coverage covers the node coverage, that's you already know. But reverse, in this case, is it true or not? If I want to do the node coverage, 1, 2, 3, 4. So this path also do a node coverage and also do the edge coverage, right? So in this particular case, the option is true. Sorry, option is false. Can I achieve a node coverage but not? So here the edge coverage, the node coverage also gives the edge coverage. So it's basically a false option. So here the node coverage also giving the edge coverage, because node coverage given by the path 1, 2, 3, 4. So that's also cover all the edges. Simple way. Yeah. Which of the following test paths achieve edge coverage? Which of the following test paths achieve edge coverage? So let us check out. It's a simple 1, 2, 3, 2, 4. So 1, 2, 3, 2, 4. So we have already seen these two edge coverage. So first one is absolutely correct. 1, 2, 4. If I just consider this path 1, 2, 4, this red color one. So we are not covering 2, 2, 3 and 3, 2, 2. So those two edges are not covered. If I go 1, 2, 3, 2. 1, 2, 3, 2 is not a valid test path only, because a test path should start with initial node, ends at the final. So this is not a test path. So you may avoid this one, last option at all. Okay, so we need to consider a tour, right? So the question is 3, 2, 3 is a tour whenever we are visiting 1, 2, 3, 2, 4. So if we are doing 1, 2, 3, 2, 4. So if you consider this red color is your main path, the red color path is your main path, that 1, 2, 4 is your main path, then your tour must be 2, 3, 2, right? So tour must be 2, 3, 2. So this is not correct. So test path 1, 2, 4, 1, 2, 3, 2, 3, 2, 4 achieves which of the following criteria? So node criteria, it will automatically achieve, because we have seen this 1, 2, 3, 2, 3, 2, 4. If you look at this, just I'll clear up the graph so that we can draw the path. Just I take this color. So which path I'm referring? 1, 2, 4. 1 to 4 is this particular path we are talking about. And another path we are taking 1, 2, 3, 2. It's 1, 2, 1, 2, 2, 3, 2, 1, 2, 2, 3, 2. Okay. 1, 2, 3, 2. Okay, then 2, 3, 2 again. 2, 3, 2. So it is repeating the loop. It is repeating the loop twice. Then finally 4, 2, 4. So we need to consider it. One is the path we have in our hand are. So we can do without doing so much drawing and all. Like it's a simple way to do this checking. So 1, 2, 4 and just I'm drawing from this image 1, 2, 3, 2, 3, 2, 4. This is what I had. Okay. So does it cover all the nodes? Does it have a node coverage? So what is the node coverage criteria? You should cover 1, 2, 3, 4. So 1, 2, 3, 4 is already covered. So node coverage is done. Edge coverage, we should cover 1, 2. We should cover 2, 3. We should cover 2, 4, which will cover 3, 2. So if they're covered or not, 1, 2 is covered here. 1, 2, 3, 2, 3 is covered here. 2, 4, 2, 4 is covered here. 3, 2 also covered here. So edge cover is done. Edge pair cover. So let us write down what edge pair we have. We have 1, 2, 3, 1, 2, 4, right? 1, 2, 3, 1, 2, 4. With 2, we have 2, 3, 2. This is a simple path, right? 2, 3, 2. I cannot have any more. Then we can have 3, 2, 4. So I think that's all. If I have to check 1, 2, 3, do I have 1, 2, 3? Yes, I have. 1, 2, 4, yes, I have 1, 2, 4 done. 2, 3, 2, yes. 3, 2, 4, 3, 2, 4, yes. So it's also do edge coverage. So it's very simple actually, if it is coming in this way. So node coverage only, no, it's also covered edge, also do the edge here. So node and edge only, no, edge cover, yes, edge cover will do. So yes. Test path 1, 2, 3, 2, 4, achieve edge coverage. 1, 2, 3, 2, 4. Just remember the path 1, 2, 3, 2, 4. So let me write it down first. 1, 2, 3, 2, 4. So what is 1, 2, 3, 2, 4? It's a 1, 2, 3, 2, 4. So yeah, it's obviously it's covering all the edges. We have seen that, right? So so yes, we are getting the edge coverage. So that's all. I have basically covered this also, the practice questions. So I want more people to be joined in the session, Zoom session, which will be regular from this week, right? So if you can ask your questions, right, whatever you have, and we can also discuss, we can discuss few more problems, right? We can solve within the meeting. So that's all for today. Hopefully we'll join next session and we'll do it together. So thank you all. If you have any problem, please post it on Discord. Thank you.